From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Morning to everyone. So did everyone get his income tax turned in on time? Any of you do it late last night? Nah, just like your homework, you probably did your income tax early. Probably back in January or so you sent it in, I would guess. Anyway, last class we were talking about transfer functions. And we went through the case of the coherent transfer function, where we found the transfer function was simply equal to the pupil function. Then we started to go through the case of determining the transfer function for an incoherent imaging system. And the first thing was that the irradiance of the image was given by the convolution of the intensity point spread function with the intensity, or maybe I should say irradiance, of the perfect geometrical image. Then we said we should go through and find the spatial frequency content of the geometrical image. And I've copied that again on a piece of paper, so if we can go here to the paper. And so last class we wrote down that the spatial frequency content of the geometrical image, G sub G, as a function of frequency, was equal to integral I sub G, U and V, e to the minus I 2 pi f sub x u plus f sub y v du dv. And then we normalized this so that at zero spatial frequency, this would be equal to 1. So we just repeated what we had upstairs, downstairs, and put in zero spatial frequency. And we get the integral of I sub g du dv. So that's the spatial frequency content of the geometrical image, perfect geometrical image. Now what we get in the image, the spatial frequency content of the image we actually get is the same result, except the I sub g is replaced with an I sub I. And we have this integral here that we saw last class. So again, we normalize it, so this is equal to 1 at zero spatial frequencies. And then I think right at the end of the class, we then took the Fourier transform of the intensity point spread function. So it's h of u v magnitude squared, and e to the minus I 2 pi f sub x u plus f sub y v du dv. And again, we normalize that by dividing by the result for zero spatial frequency. Now, we had started out by saying that the image is given by the convolution of the intensity point spread function with a perfect geometrical image. So we can use the convolution theorem here. So using the convolution theorem, we have that, get this so you can see it. This is G sub I, f sub x, f sub y, then is equal to script h, f sub x, f sub y, times capital G sub g, f sub x, f sub y. And this h here is what we call the optical transfer function. And so OTF for short. And so this was given by the Fourier transform, the normalized Fourier transform of the intensity point spread function. And in general, this can be complex. So we have a magnitude and we have a phase. And we take the magnitude of this, so say modulus and we call that the modulation transfer function. Okay. And we then call that MTF for short. So the MTF is the modulus of the optical transfer function, and then there's some phase associated with the transfer function too. Okay. So now, so this relates then the spatial frequency content in the image with the spatial frequency content in the perfect geometrical image. And so we want to look at this transfer function, optical transfer function, a little bit. And the first thing we're going to do is find a relationship between the coherent amplitude transfer function and the incoherent optical transfer function. So find relationship. And again, I'm following Goodman very closely here. So relationship between amplitude, so incoherent amplitude transfer function, and the incoherent optical transfer function. And so from last class we had that the coherent transfer function, just capital H, f sub x, f sub y, was a Fourier transform of the amplitude spread function here, h. And we have here the incoherent transfer function was the Fourier transform of h squared, so it's the intensity point spread function, and then we normalize that, just dividing by the integral h of u and v magnitude squared du dv. So just divided by whatever the value was at zero spatial frequency. Okay, so if that's true, then we can write so I'll say it follows that the incoherent transfer function is equal to integral here of coherent transfer function. Pick variables of, I guess, p and q, p prime and p and q prime times the complex conjugate of p prime minus f sub x, q prime minus f sub y, dp prime, dq prime. Oops. And again, we keep normalizing this. H of p prime, q prime, squared dp prime, dq prime. Okay, so this gives us a relationship between the incoherent transfer function and the coherent transfer function. And there's nothing wrong with this expression, but it's not the way we normally see it. And so we're going to make a little change of variables to get it into a more common form. And we're going to say that P is P prime minus F sub x over 2. And Q is Q prime minus F sub x. Oops, minus F sub y over 2. And we'll plug that back up in here, and we're going to end up with a more symmetrical relationship that h of f sub x, f sub y is equal to integral capital H, coherent transfer function of p plus f sub x over 2, comma, q plus f sub y over 2. And then over here we get the complex conjugate of h. And now it's p minus f sub x over 2, q minus f sub y over 2. And always run out of space here, but dp dq. And again, we have to normalize this. So it's just h of p and q squared dp dq. So what we have here is that the OTF is the normalized autocorrelation function of the amplitude transfer function. So I'll write that down. Still not quite the way we normally see it written, but we'll get to that in a second. So the OTF is the normalized autocorrelation of the amplitude transfer function. Okay. So I'll celebrate that result by taking a sip of coffee. Coffee today is slightly better than Thursday, but I think I'm going to look for a new coffee supplier. Okay. Well, there's nothing wrong with this, but it's not quite the way that we still normally see it. But what we normally see it is in terms of the pupil function. And remember that h here, the amplitude transfer function, is equal to the pupil function. And so h of f sub x, f sub y, is p of lambda z sub I f sub x, lambda z sub I f sub y, as we had last class. So we simply take that and plug it into the expression here, and then we will get the result that we normally see. And I like this result so well, I'll get a clean sheet of paper to put it on. So what we have here is that the OTF is equal to, well, it's equal to a mess, but it's a very useful mess. So we have P of x plus lambda z sub I f sub x over 2, y plus lambda z sub I f sub y over 2. Already running out of space here. Well, just times p complex conjugate of x minus lambda z sub I f sub x over 2, y minus lambda z sub I f sub y over 2. And then I better get in here the dx dy. And of course we want to normalize this. So we have p of x and y squared dx dy. So this is simply, if you can read my writing, is the autocorrelation of the pupil function. So the optical transfer function is given by the autocorrelation of the pupil function or given by the normalized Fourier transform of the intensity point spread function. And this is kind of a handy way of thinking about the OTF here. And if we think for a second, we have I don't know, Goodman seems to like square apertures, but I like circular apertures myself. So if we have the pupil function here, I like circular apertures, just can't draw them very well. So that's our circular aperture. We're taking the autocorrelation of that. So I'll just take the same thing, shift it sideways. And if we have no aberrations, in a few minutes we'll worry about aberrations, but if we have no aberrations, then the OTF is simply the area of the overlap. Okay? And so we start out with no overlap, and so the OTF is normalized to 1. And then we're going to have overlap here, and so the OTF is going to drop down. We'll have a curve for that in a minute. And then finally, as we separate these pupils just enough, they're just going to separate like that, and that will be the cutoff. So if no aberration, the the optical transfer function is the area of overlap divided by the total area. Again, normalizing to 1 at 0 spatial frequencies. Okay? Any questions on that? Well, let's write down some general principles of the OTF, and then we'll look at a couple of curves, and then we'll talk about physically what's happening here. So some general properties of the OTF. And there are 3 of them that we're going to mention here. First off, well, it's normalized such that at 0 spatial frequencies, the OTF is always equal to 1, regardless what aberrations you have, regardless what pupil you have. It's normalized to 1 at 0 spatial frequency. The second one here is kind of an interesting one. H of minus f sub x minus f sub y is equal to complex conjugate of f sub x, f sub y. So this is what we're saying, that the OTF is Hermitian. And how do we know it's Hermitian other than the fact we read this someplace? Well, those of you who took Gaskell's course, in between the jokes, did you learn what Hermitian was? Why something is Hermitian? And so if we think here, one way of thinking of the OTF is that it's the Fourier transform of the intensity point spread function. The intensity point spread function is real, and the Fourier transform of a real function is Hermitian. Okay? So the OTF is Hermitian. We'll use that right at the end of this chapter for something we're doing. Okay. The third one is that the magnitude of h of some frequency f sub x, f sub y, is less than or equal to the magnitude at zero spatial frequency. And if you go to Goodman's book, I think he has a derivation in there using Schwarz's inequality, showing that this is true. But I think if we just go back and think about the autocorrelation function, think about sliding the two images here, that it becomes obvious that this is true right here. Okay. So these are three general properties that come in handy as we work with OTFs. Okay, so next we want to go through look at a couple of examples of OTFs. And so examples of, well, I don't want to worry about aberration yet. That's coming in a few minutes. But examples of aberration-free OTF. I mean, often people call this diffraction limited OTF, but I claim that everything is diffraction limited, so I don't want to call it that. I'll call it aberration free. Okay. Well, let's say we have a square aperture. Now, I don't know how many of you have seen a square lens, but we're going to have one now. So we have a rectangular aperture. And of width 2W. And if we were to make a plot here of the transfer function, and if we did this first for coherent light, remember that we had a cutoff here at some frequency f naught, where f naught was equal to W over lambda z sub I. Okay, and that was 1 over 2 lambda f number. So that's for coherent light. And this is, again, 1. Okay. Now, if we have the rectangular aperture, actually, I guess it's a square aperture right now, but and we think of the OTF as being autocorrelation of the pupil function, and at least if we think of sliding sideways here, I think without too much thought we can come to the conclusion that this must be the OTF must be a straight line. Okay, and it's going to be a straight line, and it's going to go out here twice cutoff of the coherent case. So this would be 2 f naught, or 1 over lambda f number. And that's supposed to be a straight line. Okay. So it's kind of interesting here that we're going out here because it's the autocorrelation. We go out here twice the frequency compared to coherent light. We get twice the cutoff, but it keeps dropping off as we go out. So for lower spatial frequencies, the coherent transfer function is higher. Well, this one keeps dropping off as we move out. In a little bit, we'll see physically why that makes sense. That would be the incoherent transfer function. Okay. Now, I think there's limited how much interest there is in square lenses. So let's look at a circular lens. And the circular lens is more difficult. And if we go back someplace here, I mean, the problem is to calculate the area of the overlap. And the interested student, which I assume includes everyone in this class, will go through this derivation, calculating what the overlap is. And it's given in Goodman's book, but I'm not going to, it's just a little geometry problem. I'm not going to do it here. But I'll write down the answer. So this is just calculating the overlap area. So it's the transfer function. OTF is a function of frequency. If you go through this geometry, it turns out to be 2 divided by pi times the arc cosine of nu, the frequency, divided by the cutoff frequency, minus nu divided by the cutoff frequency, square root of 1 minus nu divided by cutoff frequency squared. This is for nu less than or equal to the cutoff frequency. And it's equal to 0 otherwise. And a cutoff frequency, again, is 1 over lambda f number. Now, I don't expect anyone to remember this formula here, but I do expect everyone, the 5 equations that you should remember in optics, that's one of them, I think. That the cutoff frequency goes as 1 over lambda f number. If we were to plot this, we would get a curve pretty similar to what we got for the square. I'll just copy something from Goodman's book. So maybe if we could just zoom in on this curve here. So anyway, this is how it goes out from 0 spatial frequency out to the cutoff. And it's nearly a straight line, but not quite. It's a little curve down here. And so that's the OTF of an aberration-free system having a circular pupil. And this would be the OTF for spatial frequencies in one dimension. And up above, we just show that, well, for circular pupil, this is rotationally symmetric, so it's not too exciting. But this would show what the OTF goes as a function of angle as well as spatial frequency. Okay. Any questions on that? Well, let's think for a second here. We certainly found some differences, big differences, between coherent light and incoherent light and the transfer function. And we had a little physical explanation yesterday, or Tuesday, I guess it was, about the coherent transfer function. So let's see if we can go through a similar explanation for the incoherent case. And then I'm going to try to convince you that a lens is nothing but an interferometer. Okay? So let's kind of refresh our memories for the coherent case. And so what we had here is a lens with some aperture. And for our example, we put an object over here was a grating, and that object diffracted light, and as long as the light got through the system, as long as the diffraction orders got through the system, that object was imaged very nicely over here. And then, of course, once the angle got so large that light didn't get through, then we no longer saw the object. And so the transfer function here was really unity until the light didn't get through the system. So this would correspond to frequencies where the light was diffracted at such a large angle it no longer got through the lens. Now, with coherent light, we have a point source, we have a single wavelength, and for right now I just want to say we have a point source, we have a collimate beam coming along here. For incoherent light, it's a little different story. So let's draw our lens again. And again, we have our object over here. But for incoherent light, if it's perfectly incoherent, light's coming in at all different angles. Okay? And so, you know, maybe the zero order goes along this direction. Maybe the zero order goes all the way up here. This could be a zero order. And this could be a plus or minus one order down here. Say, I'll say the plus one order. And so for small angles, the first thing we see is that light can be diffracted at twice the angle and still get through the system. Okay? And so that explains, or helps to explain why the cutoff frequency is twice as large for an incoherent system as it is for a coherent system. Because light can be diffracted at twice the angle and still get through the system. Because we're illuminating this, you know, light comes in at this angle, we have one zero angle, one zero order here, we have zero orders all the way through here. Okay? So you buy that, that's why we're getting twice the cutoff. Now we think, so we have these two beams coming in here and they're forming interference fringes over here. The lens is combining these two beams to give us fringes here, and it's giving us that spatial frequency in the image. And so for light at the cutoff frequency, or for light at the cutoff frequency, the light is going through just the edges of the lens. We're not even using the center portion of the lens when we talk about light forming the image at or near the cutoff frequency. Okay? If I go to lower spatial frequencies here, well, let's see if I have another color that doesn't look the same. I could think of light coming in here, that being a zero order, and then light being diffracted down here. And this light interfering will produce a different spatial frequency. And so that spatial frequency is produced by light leaving the lens at points separated by whatever this distance is. And so we have lots of pairs of points on the lens that contribute to this lower spatial frequency. And the lower we go in spatial frequency, the more pairs of points on the lens will be contributing to that particular spatial frequency. And so that is why at low spatial frequencies we have a larger MTF. We have more pairs of points on the lens contributing to that spatial frequency than we have to this spatial frequency. And so all this, what this lens is, you know, it's an interferometer. It's combining these beams to produce our image. And at the cutoff frequency, it's just, you know, two beams at the two extremes that combine to produce that frequency. But at lower frequencies, there's lots of pairs of beams that will produce that lower spatial frequency. And so that's a little explanation of why the cutoff frequency is twice as large, why the MTF drops off in a manner like this. Any questions? Well, you buy the fact that a lens is nothing but an interferometer? Just combining all these beams to get interference, and your image is nothing but interference fringes. Okay. Any questions? What if we have aberrations? Well, we'll write down the equation in a minute, but let's just look at this drawing for a second. If we have aberrations, you know, the light going through the lens here produces some fringes here. If we move sideways, due to aberrations, there's going to be phase differences between the two interfering beams. And so if I move up here, I'm still going to get the same frequency fringes, but they're going to be shifted sideways due to aberrations. And so the fringes produced by different portions of the lens will be in different locations, and they will tend to wash out, and so that will tend to lower the MTF. Okay. Well, let's write down an equation here for how we would calculate this if we had aberrations, how we would calculate the OTF. I guess I give this a different number here of 15.2.1. Effect of aberrations. And so we have some pupil function, P of x and y. And I'll write that as a modulus, so value times e to the I phase. And so phase I'll write as e to the I k, 2 pi over w, times whatever the wavefront aberration is, w of x and y. And let a of f sub x, f sub y be defined as the area of overlap. Okay. So as we do the shifting of the pupils, this A here is just the area of the overlap. And so if we had no aberrations, H, the incoherent transfer function, would be equal to integral over A, area of overlap, dx dy. So it's just equal to the area of overlap divided by the area of overlap at 0 spatial frequency. So that's just the pupil dx dy. Okay, so that's just writing the OTF in terms of using A being the area of overlap. Now, if we have aberrations, now the OTF is equal to the integral over the area of overlap of e to the I k, well, whatever the wavefront aberration is, w of x plus lambda z sub I f sub x over 2, and comma y plus lambda z sub I f sub y over 2. The thing I like on my computer screen is I can just move the screen sideways and I have all this other space here, but this piece of paper. Well, why don't we do the same here? We'll do that in a second here. And then minus w of x minus lambda f sub x over 2, comma, y minus lambda f sub y over 2. I'm not sure how you do this on your sheet of paper. dx dy. So anyway, it's just the integral over the region of overlap of the wavefront shifted in one direction minus the wavefront shifted in the other direction. Okay? And when we take 513, if we take 513, which now I find out, I think I warned you, I'm sorry to say it can't be at 8 a.m., it's going to be at 9 a.m. At suggestion of one of you, I tried 6 a.m., but that didn't work, 6 or 7. Didn't like that. I won't say who made that suggestion. You remember. Okay, so we just have the integral here of the what I'll call the wavefront difference function, what we called in 513. And then, of course, we have to normalize this by what we'd have for zero spatial frequency, just the integral over the aperture dx dy. Okay? So it's not too hard to calculate this. And again, we see that, we're getting this interference process. And for a given spatial frequency, we're interfering points in the pupil separated by some distance. And the problem when we have aberration is that the phase difference between these 2 points will vary over the pupil. And so this is going to tend to reduce the OTF. And in fact, we can say here that aberrations never increase the MTF. So aberrations never increase the MTF. Always reduce it. Okay? So you see how to calculate the OTF here. Now, if you're using a computer, there are a lot of ways of measuring the OTF, and again, in 513 we'll talk about many ways of measuring the OTF. But nowadays, the normal way that you would do the OTF is some way you determine the wavefront, probably with an interferometer. And then you say, well, the point spread function is a Fourier transform of the pupil function. Okay, well, we better square that. Square the Fourier transform of the pupil function. And then the MTF is simply equal to the magnitude of the Fourier transform of the point spread function. Okay. And so you just do a couple of Fourier transforms and you calculate the MTF. Now, I gave you a handout today of, I looked at 4 examples here and of aberrations. And so let's look here. Somehow my printout looks much better than a Xerox. What you see on the computer screen looks much better than this printout. So each generation we go, it gets worse. But anyway, here we looked at a pupil that had one wave of defocus. And so the wavefront aberration was x squared plus y squared. And this is the intensity point spread function for one wave of defocus. And I think when we talked about diffraction before, in the Fresnel diffraction area, we said that if we had one wave, we would get 2 Fresnel zones. We get a dark spot in the center, and lo and behold, we got a dark spot in the center. And here's it's both x and y profile on top of one another here. The y was plotted last, so that's the one we see, I guess. And it dips down to 0 here at the center. Now this was normalized such that for no aberration this would go up to 1. And so this is 0.05. So even with one wave of defocus here, we have brought down the peak intensity a lot, factor 20. But anyway, down here what we're looking for is the modulation transfer function. And the red line is what we would have if we had no aberrations. And so that's just that plot of that function that had the arc cosine and other terms in it. And this goes out to the cutoff frequency, 1 over lambda f number. And then this is what we get for the MTF for this pupil having one wave of defocus. So it drops down here to, and 0 is not that line, 0 is above the line a little bit. So it goes down to 0 here, and then it comes back up, and then it dips back down. Now, if we were to look at the phase of this, which was in the program, but I didn't plot it out here, we would see that when it goes through 0 here, the phase changes by pi. So it's a 180-degree phase change in the OTF and going from here to here. And we'll look at that in a little more detail in a few minutes. But if we just think here for a second, if the OTF changes by 180 degrees, what do you think will happen to the image? Well, I'll give you a hint. We'll see this in a few minutes here, but there'll be a phase reversal. And I can go to Goodman's book where he, see how this looks on here. Goodman has a picture of this radial grating here. And then he defocuses it. I wonder if we could actually do that here. Could we, will the TV camera just defocus on this? Okay, well, okay, maybe we can see it right here. I don't know if you can see it, but I have a closer monitor than you do. Well, that's perfect right there. Just leave it there. In fact, improve the focus a little bit. What you had before was better. Go in. Nope. Okay, well, this will, no, keep going, defocus. Whoop. I think we can stop right there. Maybe we can see. If we look here, I don't know how good your eyes are. Can you see where it goes through 0 here, that there's a phase reversal? If we try to follow this in, the black line in, then it becomes a bright line. I don't know, can you see that from your seats or not? Good. So we do have a phase reversal there when we go through the 0 and the MTF. Okay, good, thank you. Now let's image again. So anyway, when the 0 goes through here, or when it goes through 0 here, then we would get 180-degree phase change in the OTF, and we'd have a phase reversal here. So even with one wave of defocus, I mean this, at 1/5 of the cutoff frequency, the OTF, or the MTF has gone to 0. That's not very good. Defocus can kill you here. Now let's go on to look at spherical aberration. And again, I picked one wave of spherical, and that's our point spread function. As a function, the angular distance here goes as lambda over d. And so if I'd had one with no aberration here, the first 0 would be at what, 1.22 lambda over d. So if I then make a plot of the intensity point spread function, again this is normalized such that if I had no aberration, this would go to 1, and here we go to 0.08 something. But the more interesting thing is we'll come down here and look at the MTF, and it has not dipped down as badly as we had for the defocus. And so this spherical goes as x squared plus y squared quantity squared, and so it's over the center of the pupil, the aberration is not as bad, and so that's why the MTF doesn't get bad as fast as it did for defocus. Okay. But then at higher frequencies, I mean, it's zero out here. So that was one wave of spherical. This was one wave of defocus. Now what's kind of interesting is to take the spherical and introduce some defocus in the opposite direction. And so that's going to be one wave of spherical minus one wave of defocus. And so now we have something that actually looks pretty good here. Point spread function looks reasonably good. If we come over here and look at the numbers, the maximum is 0.8, and it'd be 1 if we had no aberration at all. So adding this defocus, or maybe I should say subtracting this defocus from the spherical, has helped the point spread function a lot, and so it's going to help the MTF a lot. And sure enough, when we come down here and look, I mean, it's pretty good. Okay. And this is what saves you when you go out and you buy your cheap camera. You have spherical aberration in it, but you just, when you try to focus it to get the best image, you actually defocus it a little bit to tend to cancel out the spherical that you have. Okay. And the last one I have here is for, I didn't do astigmatism, that's fine. I was going to do astigmatism, I guess I forgot to do it. The last one I have here is coma. And coma here then I wrote as x times x squared plus y squared. And so this is interesting in that it's not rotationally symmetric. And our point spread function looks like this. First, the peak in the point spread function is shifted sideways from where it would be if we had no aberration. And since this is not rotationally symmetric, when we do the MTF, we're going to get different MTFs for different profiles. And so this would be the aberration-free MTF, and this is what we get in the y direction. And if we look in the y direction, I mean the point spread function is kind of better. You know, it's definitely better in y than it is in x. And so in y, the MTF is higher, and in x it has dropped down here. And I guess I was going to do astigmatism, but I guess I didn't add that to the package here. Okay, well those are some examples. And again, these were all calculated by just taking the Fourier transform of the wavefront, squaring that to get the point spread function, and then taking the Fourier transform of the point spread function and getting the transfer function here, which in mathematics is extremely simple. You just say Fourier, and it does it for you. Okay. Any questions? Well, the last thing I wanted to talk about in this section is a little bit more on what the OTF means. And maybe we all understand it, but let's go through an example anyway and see here. So what does OTF mean? Well, really what I'm saying is, what does the OTF do to the image? And let's say we have an object which has luminance of, I'll take a one-dimensional object, I naught times 1 plus m sine mu x. So it's just a, again, a sinusoidal target here. And I wrote this as I, but I really, oh no, that's okay. So this is what we have, okay. I'm going to assume unit magnification. let's say at the OTF. Now the OTF is a function of nu sub x and nu sub y. But I'm just going to do this for the one-dimensional case. And so we say OTF as a function of frequency here is equal to the magnitude, OTF, frequency, times the phase, e to the I theta, which is a function of frequency. Okay? And let's see. I'm going to want to make use of the property at the OTF of minus frequencies. We said this was what? Hermitian. And so it's going to be OTF complex conjugate of frequency. Nu. Okay. And therefore, for the image, we can say that I of x, I prime of x, something for the image, is I naught times 1 plus, we'll write the sign as e to the I and e to the minus I. So it's 1 plus m over 2I times the magnitude of the OTF times e to the I. So we're multiplying this by the OTF. So I have a magnitude, e to the I phase. So e to the I nu x plus theta nu. Okay? So I had to multiply this by whatever the OTF was at that particular spatial frequency. So it's just magnitude times e to the I phase. And I have to do the minus frequencies here, so I'll put a parenthesis in here. Minus e to minus I nu x plus theta function of nu. Okay? So I multiply this frequency by the frequency component by the OTF. And so what we have here is that the image, I prime of x, is I naught 1 plus m OTF of nu sine nu x plus theta of nu. Okay? And so the result is that the MTF, which is equal to the magnitude of the OTF, reduces contrast. And so it reduces contrast by whatever the MTF is at that particular frequency. And the phase of the OTF shifts the frequency component. So there's a shift here in this frequency component, and the shift depends upon what the frequency is. So even though, theoretically, even though, let's say we have a very good MTF, the phase of the OTF could still mess up the image because it's shifting each frequency component by a different amount. Okay? And if this phase turns out to be 180 degrees, we're shifting that frequency component by half the period of whatever that frequency component has for the period. And so the shift is simply equal to theta divided by 2 pi times the period. Okay. Now I said in theory, we could have a high MTF And still the image could be messed up because the phase of the OTF is low. Because of the phase of the OTF shifts to different portions, different frequency components differently. But in practice, at least wherever I've checked it, whenever the phase becomes large enough that it bothers you, the MTF has already become so small that you're in trouble anyway. So it doesn't turn out to be as important as you might think it might be. Okay. Any questions on this? Another parentheses up here. Well, if you look back and look in Goodman's book, he gives credit to a number of people who did pioneering work in optical transfer functions. But unfortunately, he left out the name of one person who actually did a lot in the use of transfer functions in optical systems, and that person being Roland Schack, who does all these things and then he puts it in his file cabinet. And so Goodman doesn't know that Schack was actually a pioneer in this area because he hasn't looked inside Schack's file cabinet. Okay. But he did a lot of the, the electrical engineers developed a lot of this theory, and then with Schack came along and he realized that this could be used in optics too, and did some very good work on it, but didn't publish a lot of it. Okay. Well, that's everything I was going to say about transfer functions, and I think transfer functions are they're very useful in optics. A very good way of specifying how well a system works. And they're a lot of fun to measure and calculate and all that stuff too. Okay, but time to go on to chapter 16. Get a little more coffee. Well, chapter 16 is on Gaussian beams. And there was a handout here. If you didn't get it for class, you should pick it up after class because we're going to cover a handout pretty closely. And a lot of places you can read about Gaussian beams. They're fascinating things and how they propagate. It's a very interesting diffraction problem. And the book where I have taken most of the material that I'm going to talk about here is a very thick book called Fundamentals of Photonics. And it's by Soleil and Tisch. And it's really more, in many ways, it's more of a handbook than a textbook. It has a pretty good section in it on Gaussian beams. As I said, there are lots of other books that have good write-ups on Gaussian beams. How many of you have this book? I'll take a survey here. A few years ago, when I taught this, maybe three years ago or so, almost everyone in the class had the book because they had a sale for $1. You could buy this book. So, and it's a few inches thick. So per page, it had to be one of the best buys there ever was. But I guess they're not having that sale anymore. Anyway, I don't think you need to go out and buy the book. The notes that I have handed out to you cover material. Well, I stole it right out of the book, to be truthful, so it covers it pretty well. The interesting thing, we have a beam, and the beam is propagating along, and you'd like to have it not spread. But unfortunately, due to diffraction, the light does spread. And probably about the best you can do is to have a beam that has a Gaussian intensity distribution across the beam to minimize the amount of spreading. And so that's one reason why Gaussian beams are of a lot of interest. And another reason, of course, is that a lot of lasers produce beams that are Gaussian beams, and so that really increased the interest in Gaussian beams. Now, as we go through here, we're going to be talking about paraxial waves. And these are simply waves with wavefront normals. Making a small angle with respect to z-axis. Okay. Now before we get into a little algebra here showing or deriving the Gaussian beams from the Helmholtz equation, let's just look at some properties of a Gaussian beam. And instead of my writing these down in my terrible handwriting, since I gave you a handout listing these properties, let's just go to that handout here. So, if we could zoom in here, well, fortunately, at least some of you have the handouts. How many of you need a handout? Maybe you can hand out the handouts. How's that? I'll give you a second here to do that. So how are you surviving without basketball? Do you have any trouble? You know, I read this very interesting article in the Wall Street Journal yesterday. When I was doing WICO, I always had the dream of having a great basketball team. And at one point, I hired all these tall engineers, and this is 100% true. You know, and I had this salesman who was 6'6". Oh, it was fantastic. The problem was when I interviewed him, I looked at how tall they were, and I interviewed them for their job position, but I forgot to see how good they were at playing basketball. And this one guy who was 6'4", never played basketball in his life. Can you believe that? So anyway, I hired this group of people. I was going to have this great basketball team, and we were terrible. We played in the city leagues, and I don't know, we were just pitiful. And you know, the truck drivers would come in or something, and they'd just beat up our people. We were so nice, you know, someone would steal the ball or something, we'd give it to them, and you know, I don't know what was wrong with it. But anyway, there was this great article in the Wall Street Journal yesterday about this guy in Texas who had a company about the same size as WICO, and he loved basketball. And he just happened to run into some guy who had the dream of being a great basketball player, and he was about 27 years old or so, and you know, he just never had quite made it. So anyway, he began paying this guy some money, and they started their own basketball team. And they were a lot better than WICO basketball team. But they weren't that good yet. So anyway, there's a great article about all the problems they went through, all the tournaments, you know, where they win, where they would lose, and they would always get into the, you know, often get into the finals, and then they would just lose in the finals and all this. Anyway, made me almost want to start a basketball team again. It was great. Okay, so they all have handouts. So let's go here. The properties of a Gaussian beam. The first is the beam power is going to be concentrated within a small cylinder surrounding the beam axis, and as we go through the math here, we're going to see the size of the cylinder and how it changes as we propagate along. The intensity distribution in any transverse plane is a Gaussian function centered about the beam axis. We're going to again see how the size of this beam changes as we propagate along. We're going to see that the width of this function is a minimum at the beam waist, and it's going to grow in both directions as we go from the beam waist, and we'll have formulas that will tell us how it's going to grow. And the wavefronts are approximately planar near the beam waist, but they become curved as we go away from the beam waist, and as we get far away, they're going to be approximately spherical. In fact, we're going to see a very neat, intriguing little relationship between the shape of the wavefront and the function of position here. And then the last thing is what I referred to earlier, is that the angular divergence of the wavefront normals is the minimum permitted by the wave equation for a given beam width. And then they like to call these like thin pencils of rays. I don't know if I'd go quite that far or not. Anyway, these are 4 properties of the Gaussian beam that we're going to see. And in deriving this, we can start this, but we can't maybe get too far in the limited amount of time we have left here. But what we're going to have here is a paraxial wave. And it's going to propagate along the z-axis, so we're going to have a phase. It's going to go as e to the I, kz. And this is going to be modulated by a complex envelope, which we'll call A of r. Okay? And A of r is going to be a slowly varying function of position. Okay? And so we're going to write this complex amplitude, U of r, as A of r e to the minus I kz. And so this is going to be slowly varying as we propagate along here. And so what we're going to do here is we're going to plug this into the Helmholtz equation. So del squared u plus k squared u is equal to 0. And we can write here that A of r, as we said, I'll write it down again, A of r will vary slowly with respect to z. So there's a term, second derivative a, with respect to z squared, that we'll be able to neglect. And so what we get here in the, well, maybe I better wait until next class. About out of time here. So we're just going to plug this into the Helmholtz equation, throw away this term, and if you come back on Tuesday morning, you'll get to see what the answer is here. Okay. So with that, I think I will close for today. I think you have homework due again on Tuesday, excuse me, homework due on Tuesday. And so have a good weekend, and I will see you on Tuesday.